Hey everyone, welcome to Applied Machine Learning. And today we're going to talk about, I'm going to introduce you to machine learning. So, most of the time, uh, a lot of the times, the question I get is what is the difference between machine learning and traditional programming? And so, the biggest difference is in traditional programming, we tell the computer exactly what to do step by step. I often, in my introduction to programming classes, would bring in a loaf of bread, um, a knife, some jelly, some napkins, and a plate. And I'll tell the students, give me the instructions on how to make a sandwich. And so sometimes they give me the correct instructions step by step, and sometimes they do not, right? And so if they don't, then we may get a sandwich with like the bread's not taken out of the bag, but there's jelly on the bag. So that's traditional programming. You tell the computer what to do step by step. And with machine learning, it allows basically the program learns based on data. And so you can even look at this a little deeper. And you can have rule-based systems, which are not machine learning, and then machine learning systems, which learns from data. And a lot of the times, especially in industry, you'll see people saying machine learning when it's really they have rule-based. There's nothing wrong with a rule-based system. In fact, if you can do a rule-based system instead of a machine learning system, it's often faster. It's often more precise and faster in terms of you actually building it and also the performance of the system as well. Um, so we're going to focus a little bit on rule-based just to give you a feel for what that's like. And then we're going to move into machine learning in terms of the course of the class. But for now, let's talk about machine learning and the different types. Um, and so there are multiple types, supervised, unsupervised, and so on and so forth. For this particular lecture, anyway, not necessarily the course, but for this lecture, we're going to focus on supervised learning. Now, supervised learning and unsupervised learning are the opposite of each other. So if you're going to know what supervised learning is, and then once you know that, you'll know what unsupervised is because it is the opposite. So supervised learning is when you basically learned from data that's already labeled to predict an outcome. So you can imagine that if you want to predict whether or not you go outside and play, whether or not you go outside and play is the label. Play or not to play. In my dissertation, I tried to predict whether developers were stuck or not stuck. And those labels were stuck or not stuck. And if you notice, there were two outcomes, right? To play or not to play, or stuck or not stuck. And so when there are two outcomes, that's called binary classification. That is probably the easiest form because you're just trying to predict whether somebody is having difficulty or not difficulty when they're programming, or should they go outside or not go outside, versus multi-class where there are more than two outcomes, right? So maybe they were stuck, having slow progress, and then making progress, as an example. Um, or go outside to play now, go outside to play later, don't go outside at all. Those are multi-class examples of classification. Now, regression, I would like to talk about this, is very similar to classification. That's the last bullet point here, except regression is when you're trying to predict the actual value. So, like if you want to know what the temperature is going to be tomorrow, temperature is, you know, 70 degrees Fahrenheit, 75 degrees Fahrenheit. That is a continuous value. If you're trying to predict what the stock market price is going to be, that is regression because you are predicting an actual value. Whereas with classification, you're predicting a label. So as an example, um, for regression, you would say it's going to be 70 degrees, right? I'm trying to predict the temperature. Classification in that same example would say I want to predict, is it hot today or is it not hot today? So those are the two biggest differences between regression and classification. Both of them are supervised learning. Here we're going to focus right now more on classification. And so a practical example of classification is whether a credit card transaction is fraud or not fraud. And give me 1 second here, and I'm going to bring up um, a notepad. Give me one moment, and I'll give you access to these notes as well. This will make things much easier. Let me know if you guys like the double screens that you're going to see. Just give me 1 second. There we go. All right, so on one screen I have a blank notepad, and then on the other one I have the PowerPoint. And so if we were going to do fraud detection, then we need some way of knowing fraud detection. Let's be more specific for credit card transactions. And so our label is fraud or not fraud. Let's do a capital like that. So we're trying to predict whether a credit card transaction is fraud or not fraud. In order to predict that, we need data. And so the question is, what data, right? And so to answer this question, you actually need to look at what data do you have when a credit card transaction is made? And so typically you would have the location, like the store is an example, um, the time, the amount spent, the type of purchase, the last location of a purchase. And so all of this data, these things, these are called features. And features are predictive of the label, right? And so things that are predictive of fraud or not fraud. And so there's no perfect science to create features. Um, in fact, there's a whole field known as feature engineering where there's guidance on how to create features, but typically you would need a domain expert and also experimentation. And forgive me, guys, I cannot spell experimentation. There we go. So typically you need somebody who knows the field and then also experimentation. Now notice I'm not a fraud expert, but I do know something about credit card transactions, right? We can intuitively we know these things. And so these are called features. And these features help predict the label. This is also called a class. So if you were to look at this, let's do it this way. All right. So if you were to look at what features look like, Um, we're going to take location, time, amount spent, type of purchase, and the last location of purchase. All right. So typically you would start off with raw data, right? Like there are no um these features may not even be data in the same place. They could be in multiple storage locations. Typically information like this is stored either in a database or um, some kind of file, maybe a CSV. If you guys don't know what CSV is, CSV stands for comma separated file. It's just a type of file format, JSON. I forget what it stands for. I think it's JavaScript object notation or something like that. Again, these are just file. These are just file format types. Um, really, what I'm going to do is this. And so, typically, data is stored in raw data. Let's get more specific here. It's stored like this, and then what we do is we generally write code that will take the raw data. So we write code, and we're going to do this in this class. That's going to take the raw data and then transform it into features. And so then you would get something like this, right? Where it's more organized. And so the location could be, um, I'm just making up zip codes here. And like you could probably look at this and say, well, their last purchase was here, and this is really far away from that. So that may be able to tell you something. Um, it may not be able to, right? But basically, you would have the data in some tabular format like this, and this is read, from the raw data. And then after you have features with the raw data and don't forget the class label. So not fraud, not fraud, and let's call this one fraud. And typically you would have lots of data. That's where the term big data comes from. You don't necessarily have to have them. Um, but you can. Um, and so say like the amount of data, usually the rule is the more data the better, right? So but in this case we're only gonna have three rows just for this example here. So you're gonna have um, features, and then the idea is that you take the data plus the features, and you input this into some machine learning algorithm. And then that is going to output a prediction. That's really the basic idea. Um, that's the basic idea here. And so this process, as simple as it seems, does have several steps associated with it. So one, you're going to collect the raw data. Two, you're going to convert the data into features. Um, 3, you're going to create a model using training data that does predictions. So this step right here is basically what I was talking about here. And then you want to test the accuracy of the model using test data. So those are, I really made this simple, but those are like high level steps to building a machine learning um, tool. And so let's kind of dig into this. So we looked at collecting the raw data. We looked at converting the data into features. Let's talk about creating a model. Now, what is a model? And so, get this question quite a bit. And a model, if you think about it, if you think about like addition, subtraction, multiplication, division, we have a model on how we do it, right? We have the number line. And so the number line is our model, right? Is what we use to do addition, right? And the basis of addition is counting. And so how do we count? We count using the number line. That's not necessarily how we started to learn how to count, right? It was mostly memorization. But if you go back to the foundation of counting, it's the number line. If you go back to the foundation of addition and subtraction, it's the number line. And so you can think of the number line as a model, which allows us to, it's a specific way um, that allows us to do something. In the context of machine learning, um, a model is a machine learning algorithm that produces a prediction. That's the basic idea there. And there are so many types of models. We're going to stay close with classification and more specifically binary classification. And the easiest model to look at is a decision tree model. And I want to show you why. You may be familiar with decision trees in general. So I'm going to show you what a decision tree model looks like. And then I will explain it. And then I think the easy example is to play or not play. I think, yeah, here we go. And so if we look at this, this is probably like the most basic example. Like people use this example a lot, which is why I looked at it. Um, so if you notice, there are 4 features: the outlook, the temperature, the humidity, and whether it's windy or not. And this is for playing tennis, but you can imagine for going outside, whatever label you want. So let's just stick with playing tennis since that's what they have here. And so the label values are yes or no. Do I play tennis? Yes. Or do I not play tennis? No. And so this is the decision tree. And the way you're going to read this is if the outlook is overcast, yes, I go outside and play. If the outlook is rain and the wind is strong, no, I don't go outside and play. If the outlook is rain and the wind is weak, I do go outside and play. On the other hand, if the outlook is sunny, the humidity is normal, I go outside and play. If the outlook is sunny and the humidity is high, I do not go outside and play. So you can typically look at this decision tree and understand what it's doing. And the cool thing is, it's similar to rule-based programming because you have if this, then that, else do this, otherwise do that. So it is based on rules And well, it's not based on rules. You can read it as rules. And so it's the easiest one to look at. I'm going to give you guys all these notes as well. But let me put this in here, this link, so you can easily access it. I think it's an excellent diagram. And it even displays the decision tree, which we will get into this, not today, but we will get into the explanation. This is just a overall, like a high level overview. Um, and so um, once you have you've chosen you're going to use a decision tree. There's an there are different algorithms to build them. This is one of them, the ID3. They're different ones. We're just going to choose this for now, just because that's the one that's here. It doesn't matter in this example. And so we're going to use this decision tree. And so what we're going to do is we're going to take this data and we're going to feed it into this algorithm. Decision tree. And it's going to create a decision tree. Actually, let's do it like this. Okay. So we're going to take this data, give it to this algorithm, and it's going to create this that you see on the screen. And so now with these rules, and as a matter of fact, let's say this training data, because this is the data you use for it to create this tree. And then once that tree is created, you're going to take different data you haven't seen, and run it through the decision tree. Oops, didn't copy the right thing. To make predictions. And so now you have predictions. And so the testing data looks just like the training data, except you don't tell the decision tree what the answer is. You don't tell it the label. If you told it the label, then it's kind of cheating, right? So the training data has all of this data plus the label. The testing data is a different set of data. You should not use the same data for testing and training that does not have the label, and you feed it into the decision tree to make predictions. And so your predictions may look something like this. So you'd have actual and then predicted. And so if the actual was no, and this is for playing tennis, okay? We're going to just stay with the example that's on this page. And so the predicted is no, 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 yes, no. Um, so this will be something like this. Say yes, yes. Okay, so now that you have, and let's actually do 10 of these. 1, 2, 3, 4, 5. Let's get rid of that. All right, so we have 10 different ones. Let's go ahead and make that a no. And we need to determine how well did this work? How well did our decision tree work? And there are different ways to do this. For now, we're just going to talk about accuracy, which is equal to the number of correct predictions divided by the total number of predictions. And so we want to compute accuracy, so the number of correct predictions are 9 and the total number is 10. And so this would give us an accuracy of 90%. And there are many stories I can tell around accuracy, but typically when I say this, like I feel good about 90%. I don't know about you guys. But if you're ever talking to business people, some may not understand that 90% is good. They may think, why not 100%? And they actually have a good point because remember what I talked about traditional programming, everything is 100% right. Um, if it's not, then it's a bug and you should fix that bug, right? And there's the ability to get to 100%, even though if it's not 100%. Um, and so with machine learning, you're never, we're never going to get the current version of machine learning. I'll choose my words carefully here. We're never going to get to 100%. And so the question is 90% good enough? Right. And even bigger than that, what is good enough? Right. Is 10% good enough? Is 20% good enough? Is 30% good enough? Is 40% good enough? And the answer to that is, and I hate this answer, it depends. It depends on what you're doing. If we had a machine learning algorithm predict where the runway was so that the airplane could put its tires on there, then it better be 100%, right? You do not want a that algorithm being anything less than 100% because there is a chance that it's gonna get it wrong, and if it gets it wrong, people's lives are at stake, right? That's just like that's a very extreme example, and hopefully we would never use machine learning in that way because it's not needed. So to give you a more direct answer, good enough is you base it off of what is the current process now. So this is very important, right? Like typically you wouldn't just jump into a project and say, we're going to do machine learning. And then you've never tried anything else before. That happens. I would say that that's probably not the best thing to do simply because machine learning is very expensive. Um, and not just from a people standpoint, but a time standpoint, a tooling standpoint, et cetera, et cetera. So good enough to getting back to the point is it better than what you have now? And better than what you have now, that's the question that you're going to have to discuss with your stakeholders, right? Um, and so that's a starting point. So you always want to have something to compare it to. You don't necessarily want to compare 90% accuracy because you're going to lose, right? Or 50% or 60%. What you want to compare is what I'm doing now better than what I had. Um, and I'll give you a real life example to kind of make this a little more concrete. So I worked at a company in search, and one of the issues was when people were using the company search engine, they could not find what they needed. And so we built a machine learning algorithm that would predict the person's desire, like what they were searching for, what they wanted. Um, and then we had to see, well, how well does that work, right? So we got an accuracy, I think it was 85% or something like that. This was more than 10 years ago. And um, the question is, how well does this work? And so we couldn't just look at accuracy. We also had to look at when people search for things, are they finding what they need, right? And so we looked at click-through rate was one of the biggest things we measured. And what we noticed was that people had I think a 30% higher click-through rate when they used our machine learning algorithm versus when they didn't. So now the question is 30% good enough, right? And on the other hand, when this is very important, when the machine learning algorithm was wrong, right? What happened? How did people feel about it? And what we found was that when it was wrong, it was no worse than the current system, and so therefore it became better, right? So that's the long way around to say what is good enough. How do we actually measure? It does include accuracy, but you also have to include other things if you're dealing with a business. Um, but in terms of here, it looks like 90% is great. There's only one problem. And I don't know if you noticed it or not, but we actually always predicted no. We predicted no, and we never predicted when they were actually should go outside and play tennis. We never predicted yes, but our accuracy was still 90%, right? And the reason is there's significantly more no's in our actual data set than there are yeses, right? 90% more to be exact. And so um, this is a well-known problem. So if you think about credit card fraud, the hope is that there's less fraud, like much less fraud, than there is not fraud, right? Like, or if programmers are stuck, is my dissertation. The hope is that people are not stuck as much as they are making progress. They're making progress significantly more. There's not fraud significantly more. So this problem does come up quite a bit in machine learning. It is known as the class imbalance problem, and this is when you have a significant much more data from the majority, in our case, this is the nose data set, than the minority data set. And it causes um, many machine learning algorithms, we're going to shorten that, to be biased and predict more towards the majority. And so there are a lot of different techniques to deal with this class imbalance. Um, One of them, the first thing is to notice that you even have it. Quick story: I was doing my dissertation. I know you probably heard tired of hearing about it, but anyways, um, and I had taken my first machine learning class. We were predicting the people were stuck. This is the first time I've ever touched machine learning. And when I got done, my accuracy was 90%. And now think about it, usually a PhD takes 4, 5, 6 years. This is in year one. I have 90%. I'm like, wow, I am going to be done fast. And little did I know, I had a class imbalance problem. And so, no, Jason, you're not going to be done fast, right? That's what basically ended up happening. And so, the ways to handle this, there are several ways. I'm going to mention two, and both of them involve um, manipulating the data sets. So, one is called undersampling, and the other is called oversampling. Undersampling is when you take, um, instead of taking like all of the data set, you only take enough of, like, you split and you take, so here we have 10 examples as and then we would only take four, right? So undersampling is when you take from the data set, you only include enough so that the bias between the majority and the minority class is not that big of a deal. And oversampling is a little bit different. That's when you increase the number of the minority class. So like this would happen. And so this looks like it's cheating. And in a way, like it feels that way. It's not. There are techniques um, that help you do this. I typically tend to do oversampling, but it kind of depends. Um, but the techniques to do this, it's called SMOOT as an example. And the idea behind that, I forget what the acronym stands for. I think it's synthetic minority. Uh, let's look it up now that I almost got it. SMOOT algorithm. Synthetic minority oversampling technique. I was close. All right. And the idea behind this is you, like I said, you upsample the minority class so you get more of the minority class. And instead of just randomly doing it, what actually happens is the algorithm comes in and it looks at the data, the features at this point, and it creates features that are very similar to this. So, as an example, to kind of help break this down for you, um, right here, it may say like overcast, hot, normal, false, right? So it's gonna create what they call neighbors, which are data that is similar or close to the existing data. We'll look at this in a little more detail. Like I said, this is just kind of an overview of things to get us kicked off. Um, and so there's some ways to handle um, oversampling to handle the class imbalance problem. And so in this class, we're going to look at different, we're going to look at classification, but since the rage and everybody's focus is on chatbots, we're going to look at classification as it applies to chat-based systems. And so as you saw, the syllabus is up. So as you saw in the syllabus, and I can actually go to that as well. Actually, let me do that right now. That'll make instead of just talking about it, so you can actually see it. So in the syllabus, we're gonna look at chatbots. I'm actually gonna do another video. Post another video about chatbots and how they relate to machine learning. We're going to look at natural language processing. And the motivation for this is chatbots are all the rage with large language models and ChatGPT and Google Gemini. So we're going to look at this from a how things started standpoint and then progress to where we are now. And that's kind of the route we're going to take. Each week, you're going to have a hand-on assignment. The assignment this week is going to be to code a if a chatbot, but it's a rule-based chatbot. Again, in my second video that I'm going to post, I'll be talking more about that. The assignment will be going up online. And all of your assignments are going to culminate into one project, right? So at the end, you're going to have a final chatbot, but it's going to be based off of all of the assignments. Here's the weekly schedule. The grade breakdown. The honor code. So collaboration is encouraged, but your work must be original. So sharing detailed solutions is prohibited. There are not a lot of us in the class, so it's very easy to see if somebody did that. Office hours, you can email to schedule office hours by appointment. My goal, especially since we are a small class, is to go live every now and again. Again, I didn't go live today because I have a headache. But if you guys have any questions, I am going to open up discussion. So each lecture will have a discussion portion so that you can discuss things to make things easier. And that'll be the end of our lecture today. Hope you guys have a good day.